Welcome back, Algebra Express. We are in Marecek 5.2 now. We are going to talk about properties of exponents, and we're going to talk about scientific notation. So if we want to write out the expression x to the fourth times x squared in exponent notation, so we want to write out the definition of what this exponent means. So we're going to do 4x's multiplied by each other. And so that represents the x to the fourth. To each other. And I'm multiplying these two things together. We want to count them all up. So you have 4, 5, 6 of these things. We want to write this as a single power of x. Or as a power of a single x. Sorry. So this should look like something like x to the 6. And now we're sitting back, we're asking ourselves, how do we get from 4 and 2 to 6? And so you might figure that out. 4 plus 2. What do we have to do? We have to add these things. We have to add the exponents. So if you're multiplying, you're adding your exponents. If you're dividing, we can do the same sort of trick. We have 5x's, 1, 5 over 2x's, 1, 2. And a lot of you are probably itching to do this already without me doing it. But if I have the same thing over itself, that and that will simplify out. So there is nothing left on the bottom except maybe you could be like a 1. It's just over 1. But I have x to the third power left over. I have 3 x's there. And what could you have done with your exponents? 5 and 2 to get to 3 would be what? Top minus bottom. 5 minus 2 will give you 3. So we could have subtracted our exponents. And so in general, I kind of think of like your exponents are kind of like a step behind your base. So if your bases are being multiplied, multiplication is faster than addition. It's defined off of addition. We start with addition, we do multiplication, then we do exponents, right? If we want to talk about rates of growth typically. And we typically define them that way, right? Add, multiply, differentiate. And so this is what I typically think. Our exponents are always sort of like a operation step behind. When we're talking about dividing our bases, we're subtracting our exponents. So if we're multiplying like bases, and they didn't really say that, but these are all both x's, right? These are both x's. They have to be like bases. We can't be pulling off different variables. So if we have y to the 6th and y to the 20th, I want to use this. If you want to write out 20 different y's, you're probably going to get a hand cramp eventually. Manual strength. Plus 6 is going to be y to the 26th. The next thing I have on here is this 2 to the 3rd, 2 to the 2nd. So this should give me 2 to the 3rd. Typically, if we're going to do something like 2 to the 5th, that's just the number 32. The number 32. It's small enough. It's reasonable enough. I think we can do 32. This next one, x to the 4th, y to the 3rd times x, y squared. Okay, so the square, and we might want to note, like the square is on which one of these variables over here? It's on your y, and it should only be on your y, right? So if I want to know what exponent is on this x, this is where you're going to have to start seeing things that aren't there. There's a 1 exponent on that x. I'm making use of this and trying to rewrite things in whatever order I want. If I'm multiplying, so this is what associative property. I can drop the parentheses with the associative property. I can rewrite things with the commutative property. So I can do both associative and commutative things to this. But I can rearrange my x's together. I can rearrange my y's together. Was basically what I went on a rant saying. So I can look at my x's together, x to the 4th, x to the first is x to the fifth, and then y to the third, y to the second. 3 plus 2 can give me 5. Okay. So now we want to look at, we did the product rule, we did some multiplying, now we want to look at the quotient rule. Going to be e to the 10 minus 5. So this should be z to the fifth. This is going to be 2 to the 5 minus 2, so this is 2 to the third. That guy is also known as just the number 8. So we should be able to do those. This one might be a little trickier. So this one has multiple variables. It's got multiple, I want to say terms, but it's not terms. It's just a single term. But it's got multiple different variables in it, and it's got a constant in front of it. So if we're looking at this, and I would kind of suggest looking at these things separately. We have something that looks like 10 over 4. Fifth over x to the fourth. And then we got this thing that looks like y to the third over y to the second. Part of this is these, we don't have them in the sort of like exponent form, right? We just have 10 over 4. So we can reduce this to 5 halves. So we can divide both top and bottom by 5 halves. And if I really wanted to, I could write out 5 x's on top, 4 on bottom. But you might notice that's going to leave me with a single x on top. And if I do the same thing for my y's, I can write out 6 y's on bottom and 3 y's on top. But if I do that, that's going to leave me with 3 y's. And it's important to notice that they are on the bottom. So I have 3 y's on bottom, I have 1 x on top. And this is going for this guy over here. So the 10 over the 4, we can reduce constant coefficients. We can't do the subtraction thing like we can do with our exponents. So we have a variable for the exponents. We can do 5 minus 4, and there's a few different ways you can do this. So the way that I typically do it is it's like the larger minus the smaller. And wherever the larger was, that's where it's going to end up. So there's 6 y's on the bottom, there's 3 on top, you're going to end up with 3 on the bottom. And we'll talk a little bit more about like maybe negative exponents in just a second, and hopefully that will bring this idea around a little bit more. So we're kind of hinting at something we hadn't got at yet. Here we go. We have expressions raised to powers. So we want to simplify using the power rule. So this one, we can write out the definition. So if I have 4 x's, and I have 4 x's, and I have that 3 different times, you might be able to figure out I have 3 groups of 4. This is the same way like when we start defining multiplication with addition. This is the same sort of way we go about defining it, right? If we have 3 by 4, that's going to give me a total of 12. And if I have, what, 2 to the 4th, 2 to the 5th, so this is going to be quite a thing. You probably don't want to write out 4 different times, 5 different groups, right? So we want a sort of quick way to go about this. So if you have a base and it's being raised to exponents, the quick way we can do that is by going x to the 3 times 4 is what will get you to the 12. So we want to do the same sort of thing here. This is going to be 2 times 4 times 5. And if you I can't talk anymore. 2 to the 20th, if you type that in your calculator, it's a relatively large number. If you want to do 2 to the 20th, that might be okay depending what the context of what they're asking you. 5 and 6, I guess, is the proper number. And that's reasonable enough. Okay. And so now they're going to give us a few more problems. Okay, so word of caution on this thing. If you want to write this thing out twice, it's probably not a bad idea for this one. I shall show you something. But there's a really common mistake people make. And they'll see this too, and they'll start saying, hey, I can distribute this thing to everything in here. And if you do that, the first thing people usually do is they'll do 4 times 2. And that's not what this is. If you want to do exponents, this is 4 to the first. We're going to end up doing 4 squared. And if you write this out twice, I think it becomes a little more apparent. We're going to have to do 4 squared. So when you have constant coefficients, don't just go multiplying things, right? I guess is the word of caution. These exponents get multiplied, not the bases. So you have 4 times 4 is going to give you 16. You have x to the third is going to give you x to the 6th. y8 will be y16. Similarly here, we're trying to get at a certain property. If you want to write this thing out twice for this example, it's probably a good idea. I think it's what they're trying to get you to look at here. So if we have x to the third, that's going to be x on top. This is going to be 4 times 4. Y to the 8th and y to the 8th is going to be y to the 16th. And so if you want to maybe make a note, they're trying to get at a certain rule here, and I kind of said it with this one. We're going to do 4 squared, so if we have a coefficient, it is this to that exponent. So you have to exponentiate your coefficients, but for your variables, your exponents, you can just multiply through, right? So this is like 4 squared is what we're going to have to do. X to the third times 2 to get here, and y to the 8th times 2 to get there. Same thing here. We can sort of distribute these exponents, right, is what we're getting at. But when you distribute them, if it's a variable, it gets multiplied 3 times 2 to get to 6. If it's a coefficient, we're still doing 4 squared. Don't do 4 times 2, right? Let me say it one more time. Do not do 4 times 2. Don't multiply these things. Exponentiate them. You can multiply these things. They are exponents to exponents. They get multiplied. 4 to the 8th times 2 is going to give you 4 to the 16th. Y to the 16th. Sorry. Okay, so we have that example. Now we want to look at this. And so I kind of said it. This, try it on your own. This is a student activity, so you should be getting this on your own, hopefully. If I want to do this, I have to look at -2. And I don't want to write this thing out 3 times. So I want to jump to my rule. -2, this is going to be -2 to the third. So I have to exponentiate that. I can multiply these two. 3 times 3 is going to give me 6. Y, I don't see a power here. So I can think of it as 1. So 1 times 3 is going to give me y. On bottom, I have 3, and if you tell me 9, I'm going to be heartbroken. 3 to the third. Z to the third is z to the 3 times 3 to the 9. So I have this middle step. There's a little thing I have to do. -2 times 2 times -2. This will give me a -8. Few things, the negative is still there. I have x to the 6th, y to the third, that stays there. 3 to the third I can simplify as 27, and I have z to the 9th. So if you have a number to an exponent, you can typically simplify those things. That's about basically what I was doing. Okay. The next one. And I want you to do this right. Try this one out. There are a few different ways you can do it. So if you see me doing it differently from the way that you did it, yeah. So what? So one way you do this is you can multiply them first. So if you do that, this is x to the 2 plus x to the 3. And now doing x to the 5 times 4 will give me 20. So that is one way to do it. Another way I can think about it is you can actually distribute this. X to the 8 times x to the 12. Will that also give you x to the 20? I believe it should. So either way, you can get x to the 20th on this guy. Okay. So one more page. Now I want to talk about this exponents to 0 and negative exponents. So what the heck are they talking about with 0 exponents, negative exponents? So I think a good way to get at that is to start thinking about things that you know. 2 to the first is a good way to say the number 2. 2 squared is 4. 2 to the third is 8. Keep going on, but I think that's probably enough. I think 2 to the 4th is 16. But if I'm going from 2 to 4, and I'm going from 4 to 8, what's the operation here? Multiplying by 2. And so now if I want to get to 2 to the 0, to the minus 1, to the minus 2. If I'm multiplying by 2 going up this way, what do I do to get back this way? So to go from 8 to 4, I have to divide by 2. So I have to divide by 2. So going from here to here, I'm dividing by 2. 2 divided by 2 is going to give me 1. Oh, look, I could do this with other things too. Like 3 to the 3rd is 27. 3 squared is 9, right? 3 to the first is a really stupid way to write 3. If I want to know what 3 to the 0 is, well, I am looking at this thing. Each time I go up this way, I'm multiplying by 3. If I go here, I have to divide by 3. And so you might notice with whatever number you have, that number, the first power, is just that number. But if I'm taking that number to the 0, that number to the 0 is also 1. Okay. And I want you to think, ooh. Where should we go? To the minus thing? I think I want you to think about this just for a minute. And I want you to fill this thing out in the remainder way. So as you probably figured out, if we're going this way, we're dividing by 2. So if I have a half, this is going to be like 1/4. This is going to be a half of a half is a fourth. A half of a quarter is an eighth. So another way you can think about that is this is just 1/2 to the first power. And another way you can think about that is this is 1/2 to the second power, gives me 4. And this is like 1/2 to the third power. So another way you can also think about negative exponents is if we have 2 to the minus third and it's on top, it's going to get flipped to the bottom. And maybe I'm getting a little ahead, but if I have a negative on the bottom, it's going to get flipped to the top. So another way you can think about negative exponents is they kind of get flipped over a division bar. Same thing here. I'm going to have 1/3. I'm going to have 1/9, which is 1 over 3 squared. I'm going to have 1/27, which is 1 over 3 to the third. And so negative exponents, we're going to flip them over the division bar and make them positive in general. We typically don't like to work with negative exponents when we clean things up. So things to the 0. Whether we take 5 to the 0, this should be 1. If we take the negative 5 and we raise this to an exponent of 0, it's like this entire thing is getting raised to 0. This is 1. This one, I think they're trying to be a little tricky, right? Because this is like we're taking the 5, raising it to the 0, and then we're tacking on a negative. This one will actually give you a -1. So this one's giving us -1. So now we want to work with negative exponents, talk about how these things look. So 3 over -2, and I've already talked about this, but if I have 3 to the -2, you can always look at that thing as kind of being over 1. And if I want to make it positive, I have to flip it. So now it is going to be 1 over 3, and now this thing is positive. It should be a positive 2. So 1 over 3 squared, or I could say 1/9. That's part A. If I look at part B, I can look at this as being things that are positive are going to stay on top. Things that are negative are going to get flipped. So 5 to the -2 is going to get flipped to the bottom. Now this 2 is going to become positive. This a to the third is still on top. This b to the -1 is going to get flipped on bottom. And we're talking about b to the first power. So maybe a little bit of cleaning up I can do on this thing, but not a whole lot. This is 25, is 5 squared. B to the first, I can just write as b. Okay. I see 1 over x to the -3. So the rule with negative exponents is they get flipped. So x to the -3 gets flipped to the top. It becomes positive 3. This is all over 1. So x to the third over 1, we can just say this is x to the third. Okay, so next thing we're doing here, if we don't see exponents, we can always write an exponent of 1. So if you wanted to write an exponent of 1 on that x, you could do that. So this is equal to, I want to start out with the x to the first. And I'm just going to go left to right, top to bottom. I think is the best way to sort of get everything. That's my x, my y to the -2. Now my y to the -2 is going to go on bottom as y2. Now I come down here. I have a 3 on bottom still. And I have an x to the -3rd. So x to the -3rd is going to get flipped up top. So I can do a little bit of cleaning. I have like terms. This is x to the first times x to the third. This is x to the 4th power. This I'm probably going to write with the coefficient out in front of 3y squared. So there are a few ways to do this. So this is a negative exponent. I could go to the -1 over 3. You can distribute that with that property like we had previously, and you might figure out both of these things get flipped. That's one way to do it. To the -1 is like writing 1 over 2/3. And if we write 1 over 2/3, we have fractions and fractions. We have to multiply by the reciprocal. Another way of saying this is that you're just reciprocating that thing, right? If we go to the -1 power, or if we do 1 over a number, that is the same thing as doing the reciprocal. So there are a few ways we can do this. If we have something like this that is being raised all to the negative power, we can go and distribute things. Absolutely go in and distribute that thing just like that, like we've been doing. This is a y to the first power. You don't see it. That's one way to do it. I'm not sure if that's the way I would do it right off the bat. So another way people do these is they will account for that negative exponent first. So if we account for the negative exponent first, we can look at what, z over 2x squared y. So we flip this thing. And since we flipped it, that takes care of the negative and the exponent. And if you do this, you will get the same solution either way you work this out. You should get the same solution, I should say, right? If you do things correctly. So this is z to the third over 2 to the third, x to the 2 times 3 is going to give me 6, y to the 1 times 3 is going to give me 3. And I believe this is what z. This 2 I can clean up a little bit with z to the third. 2 to the third is just 8, x to the 6, and y to the third. So you might want to clean this up a little bit more. And we're looking at the same, but there are no terms that are like, right? So that's the key indicator that we're kind of down to the final sort of thing that we can solve this thing for. Or not solving, but simplify, I guess is the word I'm looking for. We're simplifying this thing. So a lot of times people don't know where to end the simplification. This is a pretty good indicator. All these things are different. They're all down to a single term to a exponent, right? So a little student activity, so hopefully you're working through these things on your own. Definitely expected of you. Hopefully you're doing it. So what are they doing on these that's a little bit different? We don't see it, but if we have to write things over 1, we can write things over 1. So in part A, I want to go left to right, so -3, have a -3, and if I want to take care of this -2 and make it a +2, I have to flip it to the bottom. I have an x to the 4th, and there's a few ways I can handle this. I can flip that x squared to the bottom, or I can keep it up here. I think I'm going to keep it up here. If you flip it to the bottom, you'll do essentially the same thing. And the reason I want to keep it up here maybe is that I can do x to the 4th times x to the -2. This is like 4 plus a -2. And if I do 4 plus a -2, that's going to give me overall x squared. If you flipped it to the bottom, you'd be doing 4 minus 2 with the division of like bases property that we learned earlier. -3, and we're going to square it. So now this is maybe a little bit of a tricky guy, but this minus, the minus in here is in parentheses. It is getting squared. This should be the +9. All right. Part B, again, if it doesn't have it there, you can always put it over 1. If we put it over 1, we're flipping this entire thing 1 over. And I want to do 3y z cubed. And now this thing is positive. So this is one way you can do it. There's a few different ways. Again, we could have distributed this thing first. And then flip it individually. I think I'm going to go with this approach. So we have this thing being squared. If you tell me 6, you're going to absolutely break my heart. Don't go for that. This is 3 squared. This is y squared. This is z to the 6. And I made this whole spiel about this, but this is 3 squared is going to give me 9, not 6. Don't do that. That's going to hurt so much. Coefficients get raised to exponents. The exponents on our variables get multiplied. So we're exponentiating this guy, we're multiplying these guys. It's a different operation, don't get them mixed up. Part C. So now we want to do C. Like I said, there's a few different ways to do this. So we have minus 2 over x to the 5th to the minus 3. So I think the way that I'm going to go about doing it here in the notes is I'm going to flip this thing first. And if I flip it, that took care of this negative up here. And so now I'm looking at this. I have x to the 5th to the 3rd. This is my exponent rules of multiplying by exponents. This thing down here still looks like minus 2. And I got to raise this minus 2, the entire thing, to the 3rd. So it should look something like that. If you wanted to write this thing out 3 times, that's probably not a big deal. But I don't want to do it. So let's go with this, x to the 15th. And I made a little spiel about this, but this is minus, minus, minus. It happens 3 times. So overall, this should be negative. 2 times 2 times 2 should give me 8. So you can write it like that. If I were writing this out personally, I'd probably go minus out in front, x to the 15th on top, and an 8 on bottom. So typically we don't leave the negative on bottom, but it's still correct. Usually we either bring it out front or put it on top. That's just more personal and more what we do by convention and what we use more. And this is still correct. Okay. And now we have a list of these rules that we just used. We have the product rule. So if we're multiplying 2 like bases, we're adding the exponents. If we're dividing 2 like bases, we have to subtract the exponents. If we have exponents, 2 exponents, we're multiplying the exponents. If we have multiple terms being multiplied, raised to exponents, we can put each one of those variables to an exponent. If we're dividing, we can do the same sort of distribution sort of thing. Negative exponents is like flipping it over 1 and making it positive. If you want to have 1 over a negative, it's like flipping it to the top. So if you got to put your 1, if you got to put your 1 here to see that rule, it's just flipping it from top to bottom, bottom to top. If we have negative exponents of a fraction, we can reciprocate the fraction and make the exponent positive. We talked about a to the 0 being 1, and we talked about it with 2s and 3s, but really, hopefully you've seen the pattern. This should work for any number out there, right? Any number to the 0 should be 1. Any number to the first power is just itself. Except we didn't talk about 0. And so maybe I'll mention it. But if you want to start a fight in math clubs or something, ask them about 0 to the 0 being 1. This is one of those things, is we're not talking about it in this class, but if you want to start fights, that's the way you do it. Is it because there's a bit of a debate whether this is 0 or whether it's 1, right? Because 0 times anything is 0. And depending how you go about doing math and what math you're doing, you might interpret it one way or you might interpret it the other, right? And sometimes it just depends. So if you want to start fights, that's a good way to do it. But here we go. We want the word, so this is 1,000. This is 1 million. 100th, 1,000th with the TH. So we're filling in words for what these things are. 100, 1,000, 1 million, 1 billion, 1 trillion is the next one. 1 quadrillion, 100th. Well, the TH would be 1 divided by 100. We can do decimal notation over here as well. If we want to talk about powers of 10, you might notice 100 has 2 zeros. It is 10 squared. This has 6 zeros. It is 10 to the 6. So this is going to be 10 to the, if you count the zeros, it's got 3 zeros. Count the zeros, this one has, what, 9 zeros? Now we're looking the other way. 1 over 100, this is 10 to the minus 2. So the way we're going to look at this is 1, 2. You had to move this over 2 to get that decimal in front of the 1. That's 10 to the minus 2. You had to move this over 1, 2, 3 to get the decimal in front. So here we're moving it over 1, 2, 3, 4, 5, 6. 10 to the minus 6 to get that decimal in front. And so we might notice 1 millionth is 10 to the minus 6. 1 million is 10 to the 6. So numbers larger than 1. We got, well, we know 10 to the 0 is 1. So numbers larger than 1 would be like these numbers up here, right? So 10 to the 0 would probably be right in here. These are the numbers larger than 1. Are going to be positive powers of 10. Numbers smaller than 1 are going to be fractional or negative powers of 10. Again, we said, like, look at it as 1 over 10 squared or 1 over 100, which is what they have written over here, right? This is 1 over 100 is 1 over 10 squared, 1 over 1,000 is 1 over 10 to the third. So that property is coming back up again. Depth in population. Rewrite each of the depths in populations in scientific notation. So we want to do these in scientific notation. So a good way to do this is you're counting the zeros, right? So 3, 6, 9, 12, and another one will give you 13 to put the decimal right here. So 2.2 times 10 to the 13th. So a bit about scientific notation is we want one sort of numeral in front of the decimal. So we move the decimal so there's basically one number in front of it. And that number should be a number between, what, 1 and 9, right? It should be a 9. It shouldn't be a 0. 0 is not one of the numerals we want. It's not significant. It's not telling us anything. So same thing here. We go 3, 6, 9, 12. We would have to move the decimal 12 spots. And so this is times 10 to the 12th. Same thing here. We want to go 3, 6, 9, 12. And this is going to give me something like 1.84. We move 3, 6, 7, 8. We want, let's go ahead and do this next one next, and then we'll do this one. We want to convert this 3, 6, 9. So this would be 10 to the 9th, and it would give me something like 1.39. Now we want to move things the other way, so we start with scientific notation. This is times 10 to the 7th, so we want to move this decimal place 7 times over. 1, 2, 3, 4, 5, 6, 7. So you might notice that's going to give me 2 here, but it's going to give me 6 zeros out here. So 8, 2, 1, 2, 3, 4, 5, 6 zeros. I believe that should be the number that they're looking for there. Okay, so they're talking about depth and population. And some few numbers to work with scientific notation. So they give us this atom in centimeters, and they want us to write it in scientific notation. So if we're writing this thing in scientific notation, we want to put one numeral in front of the decimal. So that 2 is going to be the numeral in front of the decimal. We put our decimal there, so now we need to count spaces. So this is 3, 6, 7, 8. I believe there are 8 places that we're moving. So this is 2.8 is the number it's going to give us out in front, times 10. And now we want to think, is this a really big number or a really small number? It's a really small number, less than 1. We're moving 8 spaces. So this overall should be negative. And now we're looking at 4.9 times 10 to the negative 11. So if we're thinking about this, is this a big number or a small number? It should be a really small number. We're going negative. This should be moving to the left 11 spaces. So if I'm moving left 11 spaces, you might notice there's a single 4 there. So there should be, what, 10 zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 spots. And so 3, 6, 9, you might notice there's 10 zeros there. And we have the 4 that makes 11 to where our previous decimal was. So this is the number that they're talking about, this many meters, I guess is what we could do. And I didn't do it here, but they were talking about what centimeters up here. Okay, so not much more. We have, we're just going to finish up talking about scientific notation. They want to talk about the average depth. And so what we're going to do is depth per population. So what they did is they took this previous page, we'll just do down, let's not get it lost. They pulled out the stats from the US. So 2.2 times 10 to the 13th is the depth that everyone that the US has, and this is the population that they have, 3.8 times 10 to the 8th. So they're dividing the depth into population to figure out how much money per person. Did I do that right? Yeah. Dividing depth by population to find out how much depth per person everyone has. So this is assuming everyone just does the same thing in the US. But they're doing this, and what you might notice if you're doing scientific notation, we have all these things being multiplied by each other. Really nice sort of way we can look at this. And so we can take the 2.2 and the 3.8 kind of separately from the bases of 10. But if you look at these bases of 10, this is 13 minus 8 will give you the 5 over here. And so that's where they're getting that from. They're doing 2.2 divided by 3.8 is giving me that 0.5790. And if we look at this, this is a really quick way to get to almost scientific notation. But this thing is not scientific notation. And so if I'm looking at this, I really need to move my decimal over one more spot. And so this is the sort of approach that I take to figure this out. So I need to move this from 0.5790, and I need to move it to 5.790. So I want this to be the same number. And so this went up. This has to go down. And it has to go down by a single decimal or by 1. So there are a few ways to kind of figure these things out. So if you figure out another way, that's good. But this is the way I sort of think about it. If that one number is going up, my other number has to go down for it to be the same number, right? And so why is it not in scientific notation? Because we don't have a single digit in front of our decimal. We have a 0 in front of our decimal, which isn't giving us anything. We want a numeral in front of there that is not 0. So we need a single numeral in front, so we're moving it so that the 5 is in front. If we do that, that number's going up, the other one's got to go down. And if you want to write this number out in standard notation and figure it out for yourself that those are the same numbers, you can also do that. You can convert it to standard notation in there if it makes you happy. Okay. And, ooh, I don't know if y'all figure this one out, but they're going to talk about like what this thing looks like on your calculator, right? And so if you typed in one of these numbers, let's say the U.S. population. So if we're doing 22,284, 900,123,456 more zeros. This was the U.S. depth they were talking about. So if we look at the depth, it's going to give me this thing. Whew. And so if you notice, they don't do times 10 to the power. What they do is they do a capital E 13. So maybe also worth noting, there is a capital E, which is scientific notation, and then there is a lowercase e on your calculator as well, which is something completely different. That is the natural exponential. Don't go pressing lowercase e. So just to emphasize, that's the lowercase e, that's the capital E, right? There are two different buttons. They mean something different. So this is case sensitive, right? Which of these does your calculator have, E or double E? I think mine has a double E button, but it brings up a single E when you press it. So if you type in the E, it's just a single E. But the key itself, I think, says EE. Sounds like a little monkey. But there it is. So we want to do depth per person, so depth divided by population. For Germany and China is what this thing is asking us to do. This is a sort of, I thought this was a student activity, but I guess not. So this is a calculator check problem, basically, is what they're doing. Germany. And in your calculator, you might figure out a way to do these without. So the German debt was 5.4 times 10 to the 12th. The population was 8.2 times 10 to the 7th. And so they want you to get a little bit of practice with doing these things in like scientific notation. So we're going to look at that 5.4 divided by the 8.2 kind of separately from this thing, which if you do 12 minus 7 should give you what? 5. And if you do 5.4 divided by 8.2, that's going to give me something like 0.65, I don't know, 85 is probably pretty good, times 10 to the 5th. And this is not in scientific notation, so I got to move this one. So this one is increasing to 6.585. This one has to be 10 to the, this one went up, this one goes down. Which, if we look at the previous one, that probably seems about reasonable. What the U.S. is 5.79. These figures are all pretty in line, right? If this is the 13th, this is the 8th, this is 12th and 7th. This one is going to be a bit different. The last thing we're figuring out is depth to population for China. So looking back at China for the depth to population, we're filling in from what they gave us in China. They said that the depth was 1.84 times 10 to the 12th, and their population is 1.39 times 10 to the 9th. So just like kind of guesstimating these numbers, if you just look at the numbers, the debt for each country is not all that much different, right? But the population for China is a great bit larger. So I think in all, if we were just kind of predicting this, we should get probably a smaller number than we got for the rest of them. So 1.84 divided by 1.39 is giving me something like 1.3. 3237, somewhere around there, times 10, and we can look at this separately. 12 minus 9 should give me, what, 3? So we're talking about 1.3237 times 10 to the third. And you might be looking at this as like, wait, I had to move those other things previously. This one, it's already in scientific notation. So that this one was a little bit nicer. We didn't have to move things around at the end. And that is the final thing that we're talking about in this section. So I will see y'all in class soon. So have fun, good luck, and study.